Everybody, welcome back to another video. Here we're going to be talking about applications of the first derivative, which coincidentally, back when I took calculus in high school, gosh, years and years ago, this was perhaps my teacher's favorite section, chapter, whatever the parallel unit was. See, he was a retired engineer, and so he was not really interested in the math, but he was very interested in using it for things, as engineers are wont to do, so he loved this. If you are still not convinced that calculus has any sort of real-world use, or there's a reason for you personally to know it, hopefully this will be one of the chapters that'll change your mind, with the other ones being the following sections. Alright, so what is the first derivative good for? Let's start that off with a discussion of increasing and decreasing functions. You might say, okay, a function is increasing if it's going up. And a function is decreasing if it's going down, and you'd be 100% right. My only question to you would be, how do we state that formally, right? Mathematically, how do I quantify this and this? Well, okay. Maybe if I put two x coordinates here, x1 and x2 here, and maybe x1 and x2 here. We see that for the increasing one, maybe both of these are functions f. For the increasing one, f of x1 is less than f of x2 when x1 is less than x2. And over here for the decreasing one, when x1 is less than x2, f of x1 is greater than f of x2. And that's going to be precisely our definition for increasing and decreasing functions. Definition. F of x is increasing on an interval I we have to talk about increasing and decreasing in terms of intervals, right? Since it only makes sense to talk about it over a region, and over a region that's all connected. If f of x1 is less than f of x2 whenever x1 is less than x2. So exactly what the picture would have guided us to. And then, corresponding definition, f of x is decreasing on an interval I if f of, and this would be for all x1, x2 in I. Sorry, missed that statement. Same thing here. If f of x1 is greater than f of x2 whenever x1 is less than x2. So x1 less than x2 means f of x1 is greater than f of x2 for decreasing functions. For all x1, x2 in our interval I. Alright, so that's a helpful definition of increasing and decreasing functions. So you might say, it might be useful to know when a function is increasing or decreasing. I mean, sure, we could check that this condition gets met, but that's kind of complicated, right? I need to pick two arbitrary inputs to the function. All I know is one of them is less than the other. Then I need to go and check their outputs and prove that the output of one is greater than the output of the other. difficult condition to check, but calculus makes it easy. Let's look at what the derivative would be along these two curves. This function is going up and corresponds to tangent lines with positive slope. This function is going down and it's corresponding to tangent lines with negative slope. So the exact theorem that you would want to be true is the sign of the derivative tells us whether a function is going up or down. So, big theorem. We have f of x to be a differentiable function on some open interval a to b. You could do closed intervals too, but it would just mess with some of the results, little endpoints. So we'll stick with an open interval. Part 1. If f prime of x is greater than 0 for all x in a to b, then f is increasing. On a to b. Part B of the theorem, if f prime of x is less than 0, exact same thing, except decreasing. So f prime of x is less than 0 for all x in a, b, aka they all have downwards going tangent lines, then f is decreasing. On a to b. And then we actually get a third part of the theorem. This is greater than 0, less than 0. Third case is equal to 0. This theorem is going to give us something for that too. If f prime of x equals 0 for all x in a to b, f of x is constant on a to b. And that kind of makes sense, right? This third case is just saying, hey, between here and here, the derivative is 0, so the function's not going up or down. Makes sense to me. Hopefully it makes sense to you too. That's the goal of this endeavor. So, you might say, why is that useful? Well, oftentimes the derivative is a simpler function than the original one, right? With polynomials, for instance, it lowers the degree of the polynomial by 1, making it easier to factor, for instance. And with several other functions, it's easier to talk about the derivative than it is about the original function. So it's helpful that information about the derivative translates back to information about the original function. It's another tool in the kit. So, as an example, let's find where f of x equal to 3x squared is increasing and decreasing. Well, according to our theorem, we only need to figure out where f prime of x is greater than 0 and f prime of x is less than 0. So we should probably compute f prime of x to start. F prime of x is So the derivative of f(x) 3 times an exponent of x power rule will end up with 6x. Okay, so that's our f prime of x, and now we need to solve. F prime of x greater than 0 and f prime of x less than 0. Okay, easy enough to solve. 6x greater than 0, divide both sides by 6. That tells us that x is greater than 0. 6x less than 0, again, tells us that x is less than 0. So, f(x) is increasing for x greater than 0 and decreasing for x less than 0. Nice and simple. This is why calculus is so impressive, right? Because it's essentially giving us easy ways to tell whether a function is going up or down. And if that function is graphing something important, like your GDP, then you might just care a little bit about whether that function is going up or down. Just a little. Alright, you might say, does this really give us all of the places where the function is increasing or decreasing? Yes. By the intermediate value theorem, a continuous function can't jump in terms of its value, right? And so because of that, we can just use this process. So, to determine where a function f is increasing or decreasing, we have a 3-step procedure. Step 1 is always going to be compute the derivative. Right, and now you can just start doing these shenanigans. But wait, what about a place where the derivative doesn't necessarily exist? There's some really nasty functions out there. There's functions that are continuous everywhere and differentiable nowhere. Or what if the derivative does something weird? What if the derivative for this function, right? Well, first it wouldn't exist there, but also the derivative jumps from negative to positive, right? We go from negative tangent lines to positive tangent lines. Okay, so we should probably account for those kind of things in our procedure. So, step 2, we're going to solve where f prime of x equals 0 or f prime is discontinuous. So places where the derivative does jump. And use this info to split R, split the number line, into intervals. And we'll see what we're doing with this with another example shortly after. Alright, so that'll be our second step. And then our third step is going to be seeing what happens in each of those intervals. Again, the fact that you only need to test one point in each interval follows from the intermediate value theorem. So pick test points in each interval. At a test point C, or rather, there goes that chalk. At each test point C, examine f prime of C to discover whether f is increasing or decreasing on that interval. Alright, give you guys a few seconds, pause the video, get this all written down, grapple with it for a bit. Alright, and now we're going to do an example with it, and you can actually see it in practice. Especially that second step, right, where we were talking about splitting the number line into intervals. What does that actually mean? Don't worry, nothing complicated. Right. Let's determine where f of x equal to 1/3 x cubed, it's 1 over 3 x cubed, minus 3/2 x squared plus 2x plus 47 is increasing or decreasing. So, nasty function, right? It would be terrible to do it via the definition of increasing, decreasing, but via our procedure, it's going to be nice and swift. So, f prime of x, step 1, compute that. Okay, well, by the sum rule, right, we can deal with each term by itself. By the power rule and the scalar multiples rule, this will be 3 times 1/3, so 1 x squared, minus 2 times 3/2 is 3 x to the first, plus 2 times x to the 0th, plus 2, and then the derivative of the constant is 0. So this is our derivative. That's simple. Now, step 2, we need to set that equal to 0 and solve. Okay, well, if we wanted to find that, we could use the quadratic formula, or we can notice that this quadratic easily factors as x minus 2 times x minus 1. Alright, the zeros of factor polynomial are precisely the zeros of each factor, so this implies that x is equal to 1 or 2. Okay, so this is step 2 done, right? This function is not discontinuous anywhere, it's a polynomial, so we've finished step 2. Except for that whole split up the number line into chunks part. Let's do it. All we're going to do is we're going to draw a number line. I'm going to mark down 1 and 2 on the number line. That's it, right? Now the number line's been split into 3 chunks. Everything before 1, everything between 1 and 2, and everything after 2. And then in each of those intervals, we're going to be looking out for the sign of f prime of x. All right, step 3, pick some test points and test the derivative there. Maybe I pick 0 as a test point. I'll use a dot for a test point. Maybe I pick 1.5, or in other words, 3/2 as my test point for that middle interval. Maybe I pick 3 for my test point there. Make it easy on yourself. Choose nice numbers. It doesn't change anything if you choose a nastier number. So you might as well make it not bad for yourself. All right, and then let's check f prime of x on each of those intervals. F prime of 0 is, okay, I'm just going to plug 0 into this function. We get 0 minus 0 plus 2, which is greater than 0. So f prime of x is positive on that interval. All right. F prime of 3/2 is plugging 3/2 into this function. You would get 3/2 squared is 9/4 minus 9/2 would give you negative 9/4 plus 2 would give you negative 1/4, which is strictly less than 0. Okay, so on this interval, f prime of x is negative. All right, let's do the third one. F prime of 3 is 3 squared is 9 minus 3 times 3 is also 9, so 0 plus 2, 2, which is greater than 0. I didn't choose those to make that happen, but it's kind of nice that it did. Plus. And now we have all the information we need to answer our question. We know that when f prime of x is greater than 0, we're increasing. When f prime of x is less than 0, we're decreasing. This test point tells us the sign for the entire interval. So this entire thing is red. And this entire middle part is blue. So, f of x is increasing on, I'm going to write an interval notation for convenience, negative infinity to 1, union 2 to infinity. So everything before 1 and everything after 2, that's where f of x is increasing, because that's where f prime of x is positive. And f of x is decreasing on the open interval 1 to 2. In between those, it's decreasing. F prime of x is 0 here and here, so we cannot include them for either increasing or decreasing, right? Since the derivative is 0 there, neither positive nor negative. Or in some senses, both. All right, nifty. Let's go a little further and see what else this is useful for, because great, we can tell whether a function is increasing or decreasing, but that's still not enough information for my taste. And maybe we'll do one more example before that. Just to really get the hang of things. All right. Let's determine where f of x equal to 1 divided by x plus 2 is increasing / decreasing. Yes, I did shorthand that as INC and DEC. Sue me. Okay, well, our procedure is the same. Step 1, take the derivative. F prime of x is equal to, okay, let's write f of x as x plus 2 to the negative first. So, by the chain rule, f prime of x is going to be negative x plus 2 times the derivative with respect to x of x plus 2. Negative x plus 2, to the negative second times that derivative. But that derivative is just 1. So this is negative x plus 2 to the negative second. Or in other words, 1 divided by negative 1 divided by x plus 2 squared. You could have used the quotient rule to get the exact same answer. I personally like the chain rule more because the quotient rule just sucks. Yes, I am biased. Okay, so that's our derivative. And now we need to solve when this is now we need to solve when this is equal to 0. F prime of x is never equal to 0. Right? No matter what I plug in for x, this is a number. A non-zero number divided by another non-zero number is not 0. So it's never 0. But there is a point where it's discontinuous, which is the other criteria we need to look out for. F prime of x is discontinuous at x is equal to negative 2, right? Rational functions, which this is an example of, are discontinuous everywhere there is a 0 of the denominator. Here, 0 of the denominator is at negative 2. Alright, so that splits up our number line nice and easily. Negative 2. And we're going to examine, again, the sign of f prime of x. And now we only have 2 intervals to check. So, only 2 test points. Sweet. Maybe negative 3 is a good test point. Maybe 0 is a good test point. Again, I'm just going to pick 0 every time I get a chance. Why make things harder for myself than they really need to be? Where's my red and my blue? Alright. If those are my test points, f prime of negative 3 is negative 1 divided by negative 3 plus 2 squared. And that's equal to negative 1 divided by negative 3 plus 2 is negative 1. Squared, though, is 1. So this is negative 1, which is less than 0. Alright, so we have a negative sign in that piece of the number line. How about f prime of 0? F prime of 0 is negative 1 divided by 0 plus 2 squared. That's negative 1 divided by 4. Right? 0 plus 2 is 2, squared is 4. So that's negative 1/4, which is again less than 0. So it looks like that function is actually going to be decreasing everywhere except at, well, negative 2, where the derivative is undefined. In fact, the function itself is undefined there. So let's actually write out the answer to our problem. And again, we'll just use interval notation since that's what's typically convenient for problems like this. F of x is never increasing and is decreasing on everywhere except for at -2. So negative infinity to -2 union -2 to infinity. Alright, nice and slick. Now, as I said, we can do more than just tell whether a function is increasing or decreasing. We can actually maximize or minimize a function. And let's do it. Well, rather, let's develop a theory for doing it, and then we'll actually do it. Okay, so we're going to title this part relative, also known as local extrema. You might ask, what's an extrema? Well, it's a good Scrabble word for one thing. For another, extrema just means extreme point of the function. So you have maximums and you have minimums. Collectively, those are called extremums or extrema. I like it as a Scrabble word. So, we've talked about increasing and decreasing, but what about those transition points, right? What about this -2 point? What about, for that previous example, the 1 and the 2? So what about transition points? From increasing to decreasing. Well, okay, let's draw a graph and get an idea of intuitively what's going on. Okay, so if we plot out the regions of increasing and decreasing just using the graph of our function, we'd say, oh, it'd be increasing, 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 all the way up till right about there. And then it'll be decreasing, down to about there. Then be increasing up again to that sharp point right there. Juggling 3 short pieces of chalk, it's not fun. Then be decreasing after that. Okay, so increasing, increasing, decreasing, decreasing. Okay, so what about those in-between points, right? Those transition points from increasing and decreasing? Well, it looks like they're at the top of their own local hills or valleys, right? So maybe there's something to that. Those transition points are going to be the relative extrema of our function. All right, so let's quantify that a little bit more. Where did mine go? All right. So, judging off of this, a local maximum or in other words, a relative maximum. Your book uses the word relative. Looks like a place, or looks to be, where a function goes from increasing to decreasing. A relative minimum, looks to be a place where the opposite happens. A function goes from decreasing to increasing. Let me get a new piece of chalk. All right, so that's your guess for what local minimums and maximums would be. You'd be completely right. And you say, okay, what's up with the whole local part of these things? Well, okay, let's say this graph continued on. This is why I use the expensive chalk most of the time. I just ran out, but this is the cheap stuff. So you can see it race in the first chalk stroke. Okay. Maybe if the function goes down there, the absolute minimum of the function might be down there. But this is still a local minimum for the function, right? Within its own relative region, it's the smallest thing around. So let's define those formally. These are our intuitive definitions. Let's give a formal definition. And then we'll see how they match. Definition: f of x has a maximum, or a relative maximum, excuse me, at x equals c if f of c is bigger than anything around. If f of c is greater than or equal to f of x for all x close to c. Similarly, f of x has a relative minimum at x equals c if f of c is less than or equal to f of x for all x close to c. So how does that square with our intuitive definition of this being a transition point from increasing to decreasing? Well, if f of x is greater than, if f of c is greater than equal to f of x for all x close to c, if you go to the definition of increasing, that means that all x before f of c have smaller outputs, and that corresponds directly to the definition of increasing. And then go to the right side, you're going from a higher to a lower place. You have to be, for you to be a maximum by this definition, which corresponds directly to our definition of decreasing. So these formal definitions do square well with our stated goal. So where does this all go into the derivative? Well, let's notice here that at any place, any x value where we have a relative extremum, then either the derivative is 0 or it doesn't exist. And that is going to be our way of quantifying maximums and minimums in terms of derivatives, right? Relative extremes are going to be places where either the derivative is 0 because it goes from positive to negative, or negative to positive, right? And has to transition between 0, or there's a jump in the derivative. You might say, okay, is that going to find all possible maximums and minimums? And is it going to find and is every point where that happens maximum and minimum? The answer to both of those questions is no, unfortunately. Here's our problems with that. Maybe we have something like, that should be more centered, x cubed. Which looks roughly like that. You know what? That's a pretty poor drawing of it. I'll draw it better to make my point. There we go. Alright. If f of x is x cubed, then f prime of x is 3x squared. So let's notice that f prime of 0 would be 3 times 0 squared, also 0, right? And that makes sense, right? We have a 0 tangent line to the graph right there, but that's still definitely not a maximum or minimum, even relatively, on the graph of our function. So we need a kind of more refined process, right? We need a way to eliminate stuff like this from tripping up our intuitive idea. So let's develop that. Thankfully, it's not going to be too hard to fix. Alright. Another definition for us. A critical number of a function f is any x in the domain of f, so any valid input to the function, such that one of these two conditions occurs. F prime of x equals 0, or f prime of x does not exist. Alright, so remember, 0 tangent, pretty easy to think about. F prime of x not existing, that's either a spike like this, or you can have a point with a vertical tangent line. right? And that's the other place where derivative won't exist. Okay, this definition is going to give us a way to find relative extrema of continuous functions. Not every function, right? Because this continuous function can do whatever the heck it wants. Right? Maybe you have a function that looks like this. Technically, the relative maximum around here is here, but that's not what the rest of the function is doing, right? So as soon as you throw discontinuity into the mix, kind of makes things go haywire. But the function is continuous on each of those chunks, so you could still get it. You could still talk about everything that we're doing here on each of the continuous chunks, just not really close to the discontinuous place. Okay, so here's our procedure. I'm going to need another piece of chalk already. To find relative extrema, relative minimums and maximums of a continuous function f. We call this the first derivative test. Wish I had an Alexa. It could be like, Alexa, place an order for better chalk. Okay, our first derivative test is going to be nice and simple. Very similar to finding those regions of increasing, decreasing. In fact, you're going to kind of be doing all of it at once. First step, compute f prime of x and find the critical numbers of f. Easy enough to do. Compute a derivative, find where it's equal to 0 or where it doesn't exist. Secondly, right, and where it's not going to exist is going to be precisely any points that are in the domain of f that are not in the domain of f prime. Secondly, we're going to examine the sign of f prime of x to the left and right of each critical number. Essentially, checking whether the function is increasing or decreasing on the sides of the critical number. And that'll tell us, hey, is it going to be a maximum or a minimum? And which of the two is it? So once you've completed the analysis from step 2, moving left to right, if f prime of x goes from positive to negative, then f of x has a relative max. Or sorry, yes, relative max. At that critical point. Now let's say we're moving left to right across some number c. just so I don't have to write as much. So moving left to right across x equals c, if f prime goes from positive to negative, then f of x will have a relative maximum there. If f prime of x goes from negative to positive, f of x, so again, we're analyzing f prime of x to gain information about f of x. So if f prime of x goes from negative to positive, f of x has a relative minimum. At x equals c. So those are our two main cases. And then the third case, if f prime of x does not change sign, so it goes from positive to positive or negative to negative, then f of x does not have a relative extrema or extremum at x is equal to c. Alright, and so that third condition essentially prevents us from cases like the y equals x cubed, right, where we had a point with zero derivative, but the first derivative would have gone from positive to positive, and therefore no relative extremum. Let's use this and do some examples. Alright, let's find the relative extrema of f of x equal to x to the sixth power. Alright, step one, compute the derivative. F prime of x is equal to 6x to the fifth. Okay, so this exists everywhere because it's polynomial. So let's set equal to 0. 0 equals 6x to the fifth tells you that 0 is equal to x to the fifth. Taking the fifth root on both sides gives you that 0 is x. So our critical numbers for f are candidates. Please note, not every critical number is a relative extremum, right? By this last condition. These are just our candidates. Our critical numbers of f are x equals 0. And that's it. Alright, and now we need to examine what happens to the left and to the right of it. So, make sure you have all that copied down. We're going to, again, just split up the number line. In this case, we're splitting it at 0. Maybe for my test points, I'll use -1 and +1. Alright? We'll see here that f prime of -1 is 6 times -1 to the fifth power. That'll be -6, which is less than 0. And f prime of 1 is 6 times 1 to the fifth, which is 6. Last I checked, 6 is greater than 0. So f prime of x is positive. Sorry, wrong side. Positive to the right of 0 and negative to the left of 0. Okay, so now by the first derivative test, f of x has a relative minimum at x equals 0. Because 0 is a critical point where the derivative goes from being negative to being positive. In other words, something like this is going on. Negative to positive. And that's all there is to it. Let's do a few more complicated examples. So, for this calculus class and any other time you need to use calculus in your life, when in doubt, take a derivative and set it equal to 0. Let's find the relative extrema of, let's say, g of x equal to 2/3 x cubed minus 8x. Alright? Take a derivative, g prime of x is equal to, okay, 2/3 times 3 is 2. X to the 3 minus 1 is 2. So we have 2x squared minus derivative of 8x is going to be 8. Cool. This exists everywhere. So we're good on that front for critical numbers. Let's set equals 0. 0 is equal to 2x squared minus 8. Divide everything by 2. That gets us that 0 is equal to x squared minus 4. You could have just added 8 on both sides and then divide by 2 would have worked as well. Now you can factor or add 4 on both sides. You get 4 is equal to x squared, which means that plus or minus 2 is equal to x. So these are going to be our critical numbers. Let's do it out on the number line. Critical points are -2 and +2. Let's examine the sign of f prime of x on those intervals. Test points, let's just choose -3, 0, and +3. Again, completely arbitrary choice. Alright, well, f prime of -3 is 2 times -3 squared minus 8. It's 2 times 9, that's 18. Minus 8 is 10, strictly greater than 0. F prime of 0 is 2 times 0 squared minus 8. 0 minus 8, -8, less than 0. And then f prime of +3 is 2 times 3 squared minus 8. Again, 18 minus 8, 10, strictly greater than 0. So, based off of that information, f prime of x goes from positive to negative to positive again. So what does that tell us? Oh, sorry, these should not have been f's over here. These should have all been g's. My bad. But name is as name does. Okay, so what does the first derivative test tell us? First derivative test says that g has a relative. Okay, we're going from positive to negative, increasing to decreasing, so we're going to have a relative maximum at x equals negative 2. And then at x equals 2, we go from negative to positive. So we're going to have a relative minimum there. So again, this kind of analysis is not bad, right? You're just taking a derivative, setting it equal to 0, or seeing where it doesn't exist, and then working from there. Let's do an example where maybe the derivative doesn't exist everywhere, so we can kind of get an idea from that. We'll do 2 more examples here, and we'll call it good. Because it's already been an hour-long video. Granted, this would have been an entire lecture. So, you know, maybe not quite an entire lecture. Maybe like 2/3 of one. Depends on how many questions people would ask. Let's find the relative extrema of f of x equal to 2x to the 4/5 power. All right. Well, take a derivative f prime of x by the scalar multiple rule and the power rule would be 2 times 4/5 times x to the 4/5 minus 1, which would be 8/5 x to the negative 1/5. Or in other words, 8 divided by 5x to the 1/5. Alright, let's do our analysis. F prime of x equals 0 means 8 divided by 5x to the 1/5 equals 0. Multiplying both sides gives you 8 is equal to 0. Sad face. So this can never happen. You could also just see it as, hey, no matter what I plug into here, it's a number. 8 divided, a non-zero number divided by a number, not 0. So we don't have to worry about any critical points from that. But do we have to worry about any other critical points? Yes. F prime of x does not exist. As where? Well, the only place that could cause a divide by 0 error. So this is our critical point. Let's do our analysis. And guess what? It's the same dang thing. Nice and convenient, because it means you don't have to learn more tricks. Number 9, our critical point is 0. I will choose as my ever so distinguished test points -1 and 1. On those regions, f prime of x is going to be, well, f prime of -1 is 8 divided by 5 times -1 to the 1/5 power. The real fifth root of -1 is going to be -1. So we're going to have -8/5. Less than 0. F prime of 1 will be 8 positive 8/5, which is greater than 0. Alright, so we go from negative to positive. First derivative test tells us all we need to know. F has a relative minimum. At x equals 0. Because we went from negative to positive. Alright. That's good. Let's keep going. One more example. Alright. Find the relative extrema of k of x equal to -1 divided by x minus 1 times x minus 2. I'll write that more center stage. Alright, much as I hate it, looks like we're not going to be able to avoid using the quotient rule. Sad day. Well, k prime of x is, by the definition of the quotient rule, derivative of the bottom not the derivative of the bottom. Goodness gracious. See, this is why I don't like using the quotient rule. Too many things to keep track of. Bottom times the derivative of the top, which will make the top -1 for the sake of convenience, minus the top times the derivative of the bottom. All divided by the bottom squared. Alright, let's move over here to finish computing that derivative. Derivative of -1 is 0. Minus -1, that's plus 1. Cool. Plus the derivative of x minus 1 times x minus 2 divided by, okay, the square distributes with multiplication, so we're going to have x minus 1 squared times x minus 2 squared. Alright. Derivative of x minus 1 times x minus 2 product rule, a little more friendly. It's going to be first times the derivative of the second. So x minus 1 times d dx of x minus 2 plus the second times the derivative of the first. X minus 1 there, all divided by x minus 1 squared times x minus 2 squared. Derivative of this whole thing is going to be 1. Derivative of this whole thing is going to be 1. So it's x minus 1 plus x minus 2 divided by x minus 1 squared times x minus 2 squared, which is 2x minus 3 divided by x minus 1 squared times x minus 2 squared. All right, let's find some critical points, which in this case are just going to be places where this function is discontinuous or 0. So, let's write it out. K prime of x does not exist at x is equal to 1 or x equals 2, right? Those are our two zeros in the denominator, so places where the derivative won't exist. K prime of x equals 0. Let's solve it. 2x minus 3 over x minus 1 squared times x minus 2 squared equals 0. Multiplying both sides by x minus 1 squared times x minus 2 squared gives us that 2x minus 3 s equals 0. 2x equals 3. X is equal to 3 halves. So all of these are going to be our critical numbers. All right. Well, we slugged through computing the derivative with our ancient enemy, the quotient rule, but we got the critical numbers in the end. Hard part's done. Now all we need to do is actually compute whether it's maximums or minimums, or neither. So I'm going to write the derivative off to the side, and then we'll do our analysis. Alright, we have that k prime of x is 2x minus 3 divided by x minus 1 squared times x minus 2 squared. Alright, draw a number line, put the critical points on it. So we have critical points at 1, 3 halves, and 2. Alright, for my decimal points, I will choose 0. Let's point between 1 and 3 halves. 5 fourths. And 7 fourths. Alright? Let's examine the sign of k prime of x. K prime of 0 is plugging 0 into here. You'd have negative 3 divided by negative 1 squared, which is 1, times negative 2 squared, which is 4. So you'd have negative 3 fourths, less than 0. K prime of 5 fourths would be, I'm going to pause it, compute that off screen, and then get back to you guys. Alright, so what you hopefully did with the calculator, and I did by hand, k prime of 5 fourths is negative 128 divided by 9, which is, again, less than 0. And now let's compute k prime of 7 fourths, which again, I will do by hand off screen. it turns out that will be positive 128. Divided by 9. Most important fact of it being greater than 0. Now you might ask, do I really have to compute those like the hard way? Compute the numerical values for me to test it? No, I could have just been like, hey, if I plug in 5/4 here, that'll be negative, positive, positive, negative divided by 2 positives, negative. Plug in 7/4 here, you get positive on top, positive, positive, everything's positive, so this would also be positive. But I did the numerical values just for you guys. Okay, what does that tell us? Well, negative, and then in between here, negative as well, and it moves to positive. Oh, I forgot my last region. Everything greater than 2. Let's do 3. K prime of 3 would be, okay, we'd have 6 minus 3 is 3. Divided by 2 squared, so 3 divided by 4 times 1, 3/4. Which is, again, greater than 0. Okay, now we can do our conclusions. By the first derivative test, K of x has a relative minimum at x is equal to 3/2 and a relative, a relative minimum at x equals 3/2, and that's it. You might be like, that's it? That's it? What about these other critical points? Well, here the first derivative went from negative, negative. Didn't change sign specifically, so no relative extrema. Ditto at x equals 2. And that would make sense, because if you were to graph if you were to graph k of x, it would give you something that looks roughly like something that looks roughly like that, right? So it makes sense that 1 and 2 would not be critical points, since the function itself isn't even defined there, much less the derivative. Alright, I know this video was long. Thank you guys for sticking with me, and we'll be back next time with applications of the second derivative. So, get more derivativity. Have a great rest of your day, guys.